Here we are in this part 2 of our look at simple beams and the flexure formula. And today I want to show you how we'll take the flexure formula and use it to calculate the modulus elasticity of the beam, that simple beam that your instructor will give you. Again, this is in preparation for building your truss bridge models that you'll be testing. So I want you to have some sense of the stresses and strains that are going on in the members of this bridge. So last time I showed you the simple beams that you'll be given. You'll be given small little simple beams like this that you'll be testing. This one from last time, if you'll notice, I've kind of taken it past the proportional limit, where this now has taken this beam has taken a permanent set. It's now not returned to its original shape. So this is the kind of stuff we're looking at. Maximum load, proportional limit load, deflection in the flexure formula. That's the kind of stuff that we're going to be studying. So you guys will be given, if you're doing this in a classroom setting, a simple beam like this. This happens to be a fir beam, a number 2 Doug fir beam. So you'll be given a simple beam like this, and you'll use a bucket of sand like this to load it. It's probably going to be the easiest. You'll set up a system like this, and you'll calculate with your dial caliper. You'll get the width of the beam, the depth of the beam, the length of the beam, and then you'll use a dial indicator to get the deflection, the Y value of the beam as it deflects, and you'll load this beam with sand you'll go past the proportional limit to the maximum load, where you sustain failure like we did in this beam with a universal testing machine, again up in Humboldt State when I took my engineering class up there, and we loaded it with their universal testing machine. So if you have access to that kind of equipment and facilities, that's the way to go, is to take, get a simple beam like this, take it up there, use their equipment, and you get much more sophisticated data. So anyway, in this little lab, you'll be doing this kind of thing if you're doing it in the classroom. So I've already got a little bit of sand in the beam, so I would continue to load it. Okay, I'm loading it. You can watch the dial indicator, and you'll load it. Now I would slow down. A little bit of dust from the sand there. I would slow down at this point, because you want to get the load data as accurately as you can. So I would slowly load it until it fails. All right. I'm not so sure that's failed yet, but so I'll stop there. I would slowly load it till it fails, and you'll hear the crack, and you've taken it to the maximum yield point. So here's some data on a real fir beam that we took up to Humboldt State and got the data up there. So it was a beam similar to this. It's the B dimension again. The B dimension this way, 1.5 inches. The D dimension this way. The depth of the beam, 1.5 inches. The length of the beam was 14 inches. It took a load of 1,975 pounds, and it deflected 140 thousandths of an inch. So with that data now, what I want you guys to do is use back to the flexure formula again, which is simply a formula used to look at a centrally loaded beam and look at the stress strain data that's going on with that beam. So we last time talked about the flexure formula. So the modulus elasticity is 1/4 P primed L length cubed, deflection times B, the width of the beam, D, the depth of the beam cubed. Okay. Now again, if you remember back to our graph of this data, as you load the beam, load, this is this slope is a constant. That's Hooke's law. I still have the definitions of stress and strain on the board. P prime is the load at the proportional limit. When you've reached the point of no return where this material is now not going to return to its original shape. P max is the maximum load sustained at failure. Okay, so this beam is still not quite failed. I was giving it a second. And you guys will continue loading it until the beam fails, and then to get your load data, again, this will be rough data doing it this way, but you should still be able to verify the modulus elasticity of this material. And again, every material will have its own E value, and that's just simply a measure of the stiffness of the beam or how elastic the beam is, whatever you want to say. Is that data important in building bridges and stuff? Again, yes, it is. You would want to know. Like this hickory beam, again, has a high E value. Okay, it's pretty stiff. So this would be a totally different beam up here than this Doug fir beam. Okay, and it'd be a totally different beam in your house or in a bridge and in any kind of structural situation. So anyway, with the real data we have here from a beam we did just recently, I want to calculate the E value of this fir beam. So this is the data for a fir beam. Okay, so I'm going to just equal 1/4 the load at the proportional limit. So this would be P primed actually is 1,975 pounds. Okay, the length of the beam was 14 inches. Okay, and this is cubed. Okay, we divide that by the deflections. What did they say? 140 thousandths. So the deflection is 140 thousandths of an inch. The B value is 1.5 inches. Again, the B value is the width of the beam. How wide is your beam? We'll talk in a minute about which is a more important piece of data to know on a beam that you're using for a bridge or a floor system or something. The B value or the D value is going to be the D value because it's cubed in this flexure formula. So we have in our data here 1.5 inches cubed. Okay. So now before we go any farther in calculating the modulus elasticity of this fir beam, and again we're trying to verify it with the tables. Like you'll have a textbook, you go online and you'll have a textbook table that your teacher will hand out to you, and you can do your test, do your experiment, and test, verify the E value that they're showing you in the textbook tables. What was I going to say about that? I don't remember. Oh, units. Okay, so let's look at the units and how this works out. Okay, so you've got inches cubed cancels inches cubed, so we're going to end up with pounds per square inch, right? So the data down here will end up with, pounds per square inch, or PSI. Okay, it's a familiar term to most of you guys. So if you do the math, I won't spend a whole lot of time doing the math on this. You're going to cube 14 and get 2,744, and you're going to cube 1.5 inches and get the number you get. So you guys can do the math. So this data comes out to 11,605 pounds per square inch. Okay. So that's a huge number. Again, all it's telling you, the modulus elasticity, is telling you what is happening in the fibers on the very upper and lower part of this beam. What is going on with that? Again, just gives you a sense of how stiff this beam is compared to another material. And there's an E value for steel. Actually, when you guys get to the West Point Bridge Design program to design your truss bridges, one component, a very powerful program, one component of that program is you can click on the material. You're going to be using carbon steel or high quenched alloy tool steel, and different materials. You can click on the material of the different truss members and go and see what is the E value of that material. So it's a very handy engineering number to have. In the textbooks, they're going to round this off to, they're just going to say 1 point, what is this one going to be, 1.9, it's times 10 to the 6, and a lot of times in the books you'll just see 1.9. You'll just see the E value of this fir beam is 1.9, okay? Again, huge number based on the data. So 1,975 pounds on a beam this size being loaded kind of gives you a sense of it's a fairly strong material, and that E value would tell you if I build my bridge out of fir or pine or oak or hickory or whatever, what is going to be the difference in the load carrying capacity of this structure. Okay, so enough of that. Now, I want to do a couple other little equations right here. So we just verified the E value of a fir beam. You go to textbooks, you go, yes, I did pretty well. Now, when you do your experiment, you're going to get pretty close. Now, again, if you do it with a bucket of sand, and you'll have to get the weight of the sand, you can use a triple beam balance, you can use a bathroom scale. And again, the load data will be suspect. If you use dial calipers and dial indicators to get your other measurement data, that'll be pretty accurate. So you'll be amazed at how close you can get here. Okay, now if there's two, and I'll do this kind of quickly. The real experiment is to verify the E value, but there's two other equations that I want derivations of the flexure formula that I want to show you. Okay, so we're going to have the fiber stress at the proportional limit, okay, equals 1.5 times P prime L divided by BD squared, all right? So you can, at the proportional limit, again, where you reach the point of no return, I've stressed this thing, and it's not going to return anymore to its original shape. You've gone beyond the proportional limit. So you could figure out at the proportional limit, at that point, what is the stress there. So again, you could plug data into this. We have all the data for this one Doug fir beam that we did. So what the data for that is, if I plug in the same data, I would end up with equals 12,289 psi. Again, this is a whole class in itself. This will just give you a sense that what is the stress really in these fibers when you reach the proportional limit. The next one is an interesting number to attain to. So you can calculate the modulus of rupture. So modulus, again, the word, just measure of rupture. Okay. So that formula is MR equals 1.5 P max L divided by B D squared. So this would tell you modulus of rupture. It's going to tell you, and again, you're going to be getting, your teacher will hand you out in this course. I've included this as a handout, so you'll get this handout. It's gonna, be a handy little resource for you. So the modulus of rupture, the maximum bending stress sustained at failure. So this beam still has not failed, so it's a pretty elastic material actually. It's not going to take a whole lot of more sand to get that to fail. So anyway, if we want to calculate the modulus of rupture, again, you plug in. Now this you would have to get the universal testing machine can tell you the data of when the material has reached the proportional limit, P prime. So in this case it was 1975, and it was also, and again there's these gauges, these dials on the gauge that are recording this data for you. So you won't be able to do that in this kind of simple experiment like this, but you could guesstimate and get pretty close. So the P max for this fir beam was, what is it? The P max was, is 2,190 pounds. So P max equals 2,190 pounds. All right. So so again, that's the maximum load sustained at failure. Okay. So if you want to calculate out the modulus of rupture, you're going to go through this math again, and it comes out to 13,627 psi. Okay, so again, you'd be plugging the data back in here, and you'll have a little test at the end of this unit to see if you can calculate, pretty simple calculations here, calculate some of these values for the material you're using. So that would be the modulus of rupture. And then the last one that is more interesting to me is, and again, derivations of the flexure formula is how do you calculate a safe working load for a beam? Let's say this is, you know, the river gorge, you know, going to your house. You have to get across this river. So you're going to throw a board down. You got a big beam or a tree or something. You're going to throw it across there. Well, what would be the safe, if you know, if you know what the load of the beam is? I mean, if you know, the length of the beam, the dimensions of the beam, and all that. What is a safe working load for this beam? So this is a kind of a handy thing for what we do in our engineering class and our architecture class. So safe working loads. Okay. And again, this is all kind of spelled out in the Uniform Building Code too, building code books that we use. But you can calculate it for yourself. And this is again a safe working load. This is all being kind of pre-engineered for you, so this is this is a doable deal. So the equation is load 1 over big K. No, that's little k. There's two constants that we've talked about. So big K is a quarter, and little k is 1.5. So and actually I haven't been doing that all the way throughout this, so I'll just go ahead and forget the constants. So so safe working load 1 over 1.5 times FB. Okay, I'll talk about that. BD squared, okay, L. Okay, so this is kind of an interesting thing. The FB is data that you can get directly from textbooks, and what the FB is it's the well, here it is right here. Well, the FB is the maximum allowed bending stress, and you're not going to be able to see this, but in the Uniform Building Code, you can look this up online and other places, but it's the FB is going to be in your little floor joist span tables. So you can go, I've got a 2x6 that's spanning, 10 feet or 20 feet or whatever, and you go down here, well, below, and it's 16 inches on center, so below the little span information is going to tell you what the FB value is, and then there's notes at the bottom of these tables. So note the required extreme fiber stress and bending FB. So you find out what, for Doug fir, what is the FB value, and it just happens to be the FB value for Doug fir, I'll put it here, is 1,450. Okay, PSI. So that's the FB value of a Doug fir beam. Okay, so you'd look that up for each material. Okay, so again, you can plug in the data and do the math. And so this is kind of an interesting scenario. I actually changed the data just so you get some real data when we actually did this, I think. So we had a 6x14. Okay, we had a 6-inch by 14-inch Doug fir beam. It was 30 feet long, okay? So 30 feet long, okay, you have to convert that to inches, 360 inches, okay? So if you have, so we're trying to calculate out, you know, what is this load, okay? What is the load it can carry, okay? So so if you plug the data in here, we don't even need the deflection data for this one. So if you plug in the data, I know what the FB is. It's 1,450 pounds per inches squared, okay? And you plug it in. I'm going to run out of room here. The B value of this beam was 6 inches. The D value was, what did I say, 360 inches squared, okay? And this is, so the load, the safe working load would be 1 over 1.5 times, all right, times this, and the length was, no wait, D value, I got that wrong. The D value is, what did I say, the D value is 14 inches, okay, squared, okay, and the length was 360 inches, okay. So again, if you cross out inches squared, you end up with pounds per, you end up with pounds. You count inches squared counts as inches squared, so we've got and we've got inches cancel inches, so you end up with pounds as a unit. So anyway, the P value, the maximum, you know, the safe working load for this beam is 3,157.78 pounds. Okay, so kind of interesting to go. Okay, I've got a 30-foot long 6 by 14 Doug fir beam. I look up the FB value of that material. What is the maximum fiber stress and bending at that material? Calculate it out. You can say, well, I can throw this 6 by 14 beam over my river and it's going to hold 3,157 pounds. Good enough? Not good enough? Now this is a safe working load. It's not going to fail at 3,157 pounds. It's not going to fail at that load, but you will be, if you go past that load, you're going to be getting dangerously close to proportional limit. You know, get a permanent set in the beam, which you don't want. So it's a pretty interesting calculation to be able to do. Okay, so enough of that. You'll use this this little information to do this simple test. Verify the E value. You could actually verify some of these other values as well. Modulus of rupture, fiber stress at the proportional limit. And then with that information in your mind, you'll go off and build your model truss bridges, and you'll have some sense of this whole stress, strain, modulus elasticity scenario that's going on in this bridge when you load that bridge. Okay, thank you. Have fun.